name is José, and I'm a postdoc at the section for wind turbine structures at the Department of Wind Energy, Technical University of Denmark. I'm going to tell you today a bit about a tool we have developed here at our section, the BEAM cross-section analysis software, BECAS. And I'm going to give you an overview of its capabilities, and I'm going to go a little bit into more detail in some of the recent work we have done on the calculation of strain energy release rates using the VCCT method for fractured beams. So the background, as I told you, BECAS is an open source beam cross-section analysis software. This is a general tool for analysis of most types of beam cross sections. That is, it handles arbitrary types of geometry and materials with any type of anisotropy. Most of the work I'm going to present to you today is applied to wind turbine blade design, since that's the work we carry out here at the section. It's written in MATLAB, and we give access to the software repository. That means the source code for free for academic use, and we ask for a small fee for commercial users. The development of BECAS was essentially motivated by a wish from our colleagues running air elastic simulations to have a more accurate representation of the blade structural response. This is to say that usually when you want to study the entire turbine, as you see here on the left, you use air elastic codes, and in most air elastic codes, or in the specific case of our HOC2, the in-house code we use, the entire blade is represented using beam finite elements, which are usually represented like this. We are mostly interested in the beam finite elements that are used here to represent the blade. So this guy here. And essentially what we want is to get these elements to be able to represent accurately the response of the real structure. So usually one of these elements represents a part of your blade. You can see here, this would be a section of a blade, which is delimited by two cross sections. And this beam element is supposed to be able to represent the way the blade deforms, the section of the blade deforms. The development of the beam finite element model these beam models are usually generated by first determining the cross-section stiffness and mass properties as a pre-processing step, so to say, and then integrating those properties along the lengths, you're able to generate the beam finite element matrices. So really the problem of developing accurate beam finite element models to represent the blades comes down to in large part comes down to an accurate determination of the cross-section stiffness and mass properties. So you could have a cross-section, as you see here, where you have the shear webs, you have an aerodynamic shell, the color code here representing different materials, and you want to be able to characterize or represent all of these geometrical and material aspects in your beam model. So while in the past you have been using it, simple models have been used to determine or to estimate the properties of the cross section. These are now not sufficient. Essentially, designers are looking for more accuracy. One clear example is the estimation of the torsional stiffness of the blade, which has not been important so far, but it's becoming more and more important as blades become larger, and stability constraints like flutter become important for the designers to estimate. The other aspect is to be able to correctly account for material anisotropy, the laminated composite material properties accurately estimate the effect of the orientation of the fibers, for instance, in the response of the blade. So in fact, if you imagine that this is our blade with all the different material properties and the complex geometry, we want to be able to account for all the effects when we estimated the cross-section properties and ultimately when we then generate the beam finite element model. And that's what BECAS was developed for, to be able to account for all these geometrical and material effects. So one example of the workflow, or one side of the workflow we have developed for wind turbine blade design using BECAS is the one presented here schematically. So you could imagine that you have a structural model. This could be drawings of the blade. It could be a shell finite element model of the blade. And what you're going to do is you're going to cut this model in sections, cross sections of the blade. You're going to define a 2D finite element mesh of that cross section, where the material properties are defined at each element, and the geometry is defined by the finite element mesh. Because using that will determine then the cross-section stiffness and mass properties, which are used to generate the beam finite element model, which is then fitted into the beam assembly here, representing the blades in your elastic analysis model. The motivation to use BECAS is, as I said before, and I summarize here again, is the ability to account for arbitrary cross-section geometry, the ability to correctly account for the effects of material anisotropy, and essentially the increased accuracy you gain by using such a tool. So you're able to much better estimate the overall structural response of the blade. The outcome is the full representation of 3D behavior of the blade, the ability to consider new effects in aeroelastic tailoring, and here one of the motivations was controlling the material properties to tailor the structural response and ultimately the aeroelastic response of the blade. And also, one thing that we have observed is that now you can have a seamless integration with the aeroelastic analysis tools. So now you have a continuous level of fidelity all throughout, from the structural model all the way to the aeroelastic analysis. So examples of the results we have obtained or capabilities within this workflow. A typical exercise is to determine the cross-section stiffness and mass properties and locations of shear, elastic, and mass center, and the elastic axis, which you see here for different sections along the blade. You can also model the entire blade and analyze the structural response of the blade using the beam model. So what you see here is many sections, and there's a beam finite element model running all along, where you use the beam finite element model to represent the blade and determine the structural response. In fact, we have used this workflow for the recent design of the DTU 10 megawatt reference wind turbine blade, which is what you can see here. And much of the results have been validated against the shell finite element models. We have also used BECAS to do structural topology optimization of wind turbine blades. So this is an idealized blade at this point. We have a cross section, which is as you can see here, which defines our design domain. We have meshed it, and we look for distributing different materials in this section, and we can determine then the structural topology. So everything that is white here is void, so no material, and wherever there's a line, there's material. We are able also to choose from a given or predefined set of candidate materials or laminated composites in different directions. So in fact, we are able to both determine the structural topology and also determine the optimal fiber orientations and material distribution in the wind turbine cross-section. These are preliminary results. We are now, this is ongoing work. We are now extending this to consider many more sections along the blade. Here we assume that the aerodynamic shell is represented, is a separate bronze, is represented outside the design domain. We're mostly interested in distributing the material inside the cross-section. Second part of the workflow is what we call here the strengths analysis. So essentially you could imagine that you have done your air elastic analysis, and a typical outcome of the air elastic analysis is the transverse forces and moments at a given section of the blade. So based on this signal, you're able to plug it back to BECAS. For a given section, you use the cross-section finite element mesh of that section and to represent, for instance, the stresses at a given detail of the blade. The motivation here is to be able to analyze the 3D strain and stress components at a much lower computational cost, and also you're able to apply the transverse forces and moments directly from the elastic analysis code without having to go through complicated or complex approximations using the shell model, for instance. The outcome is new possibilities in terms of stress analysis, because with this gain in computational efficiency, now you can consider do fatigue analysis at the material level. And once again, we also obtain this seamless integration with the elastic analysis to do. Once again, we have this continuous level of fidelity throughout the whole workflow. So one example here where we did the stress analysis at a detail here of a cross-section. And what you can see here is different stress components. You can see the stress through the thickness for each of the different components. We have used this result to validate the stresses coming out from BECAS. So we can see here there's different materials and adhesive uniaxial fibers from the cap and the sandwich panel from the shear web. And here on the right, what you see is a comparison between the stresses. And this is the 1-2, in fact, the strains, the 1-2 strain. So the in-plane shear strain acting on this detail of the structure in a comparison between Abacus and BECAS results, and you can see there's a very good match between the two. We have also recently implemented some failure criteria, maximum strain, maximum stress, and Psi-Wu specific for laminated composite structures. And we show the results here for a simple example where we compare BECAS with the ANSYS in this case, and the lines really are on top of each other, so you cannot see the difference, but black here would be BECAS and gray would be ANSYS, and you can see there's once again a very good match. The material here is oriented at 17 degrees and 17 degrees in fiber plane orientation, so that's a very not so easy example to get the correct results. So now I'm going to tell you a little bit about some recent work we have done on fracture analysis using VCCT, or the virtual crack closure technique, which we implemented in BECAS. I'm going to tell a little bit about some basic concepts from fracture analysis, and I'm going to show you some validation work we've been doing. So fracture cracks are essentially present in many different fields. You can see here for ships and or for human bone. We are mostly our work is mostly motivated for the analysis of cracks and D-bonds, or cracks generated by D-bonds, or it could be adhesive D-bonds here in the trailing edge on wind turbine blades, for instance. So there are different fracture modes which we'll mention, and here we have mode 1, which is this here on the left. We have mode 2 opening, which is an in-plane shear type of crack opening, and the mode 3 out-of-plane shear here, as you can see. So in our case, this would be the cross-section here, and so this is how we would define the different modes. Strain energy release rate, in this case, is defined as explained here, is the energy dissipated during fracture per unit or newly created fracture surface area. This is standard textbook definition. There are many different ways of determining the strain energy release rate. You can do it through experiments. A very common way is also the J integral or the virtual crack closure technique, which we will use here, and which essentially using a finite element mesh based on the nodal forces at the crack tip and the displacements of the elements in front of it, we are able to determine the strain energy release rate. In a way, this is a fairly straightforward approach, and it's mostly simplicity that is so appealing. The motivation for doing fracture analysis using VCCT and BECAS is the high computational efficiency once again, and the fact that we can reach quite a high accuracy. Also, we would like to highlight this fact is that we are able to analyze mode 1, 2, and 3 crack openings. So this, although it's a 2D mesh that you see here of a cross section of a fractured beam, in fact each of the nodes has 3 degrees of freedom. So we are able to represent, as you see here, the mode 3 crack opening induced by a torsional moment here in this case, which normal 2D models cannot. So the outcome is a strain energy release calculations for a general class of beams, so arbitrary geometries independently of material anisotropy, and this this gain in computational efficiency opens up to the possibility of, for instance, doing fatigue analysis using strain energy release rate information. So I'll present you some validation results. We have compared the results from BECAS against analytical results, and we have compared it against 3D solid finite element models in Abacus using VCCT and J integral calculations. We have considered, or will present here, results for 3 different types of cross sections. So here on the left is just a circular cross section, so essentially it's a cylindrical shaft with a crack. We'll present another result where we have a bimaterial square cross section with a crack here in the center. And finally, we'll present results, because this is the most challenge of examples, when you have a crack at the interface between 2 materials. We will look at the cantilever beam, so it's clamped on one end and has the loads are applied here at the tip. So in this phase, or in the case of BECAS, this is done with a beam finite element model. So there will be a beam finite element model running here, which would be constrained at one end, and the loads would be applied here at the last node. We assume that all cracks run all throughout the length of the beam, as you can see here, and we are calculating the strain energy release rates here in this crack tip. We calculate, in fact, at the central section, so that we minimize the effects of the boundary conditions, so to make a fair comparison between the 3D and the beam model. So an example of a comparison, we have here the cylindrical shaft. There's a crack here. This is an example of the deformed shape. There's a tip transverse force in the y direction, and what you see is a mode 3 crack opening. So this face moves forward while this one moves backwards, and you have there then the strain energy release rate is calculated there at the crack tip. And what we compare here is we have here the analytical value, the Abacus value calculated using VCCT, the Abacus value calculating the J integral, and the BECAS value. And you can see there's a very good comparison between BECAS and the analytical result. Very good comparison between BECAS and Abacus, and BECAS and the J integral in Abacus. Next example is the bimaterial cross section with a crack at the center, and we see here this is a tip bending moment. So a bending moment applied at the tip of the beam, and there's shear stress mode 2 crack opening. So this face slides up while this one slides down and the crack is there. And once again, a very good match between BECAS and Abacus, both using VCCT and the J integral. The last example is our bimaterial square again, but now with the crack at the interface. There's a transverse force at the tip, and we have a combination of mode 1, 2, and 3 crack opening. So what we present here is the total strain energy release rate. And there's a very good match once again between BECAS and Abacus using VCCT. Finally, I will just show you a little bit or a good example of the effect of the boundary conditions on the 3D model when you start doing this type of comparisons against the beam model. So remember, this is the case we are looking at. You have the constraint in one end, the loads are applied on this end, and we have been showing you comparing results at the central section here. So we have measured the strain energy release rate at the crack tip in this section, central section here. Now we want to show you now is that how the strain energy release varies along the length at the crack tip along the length of the beam. And as you can imagine, there's some boundary effects here in the 3D model as due to the constraint, and there will be some effects here at the tip due to the loads. So this is what you see. This is an example where we have the bimaterial beam with a crack at the center, and this is for the load, the transverse load in the y direction, and I'm showing you the G1, that's the strain energy release rate associated with mode 1 crack opening. And this is the length of the beam in the x-axis in both plots, and here is the value of the strain energy release rate. So this is the BECAS case, is the bold line here, which you see. There's a variation along the length because there's essentially a variation of the transverse, of the bending moment along the length of the beam, which results in a variation of the strain energy release rate. Now the Abacus model sees, you can see the effects of the boundary conditions here at the beginning. It's interesting to see how far into the beam these boundary conditions, how far into the beam you can see the effect of these boundary conditions. But otherwise a very good match all throughout the beam. Here's another example now for mode 2 opening, where you should have 0 all along the length, and you can see here the deviation due to the clamped boundary conditions here on the left and the effect of the load application here on the right. We believe that the cases we have been presenting, the crack is placed, in this case, placed at the center of the cross section. This cross section will have will behave a little bit like an open cross section, so the warping will be relatively large, so the constraints will have a more significant effect. For wind turbine blades, for instance, where you have a closed cross section and you would put a crack, for instance, or look at the crack between the adhesive bond of the cap and the aerodynamic shell, this effect should be significantly reduced. So the conclusions, we have shown you the workflow for BECAS, general application of workflow of blade design. We have gone a little bit more in depth into some recent work on fracture analysis using BECAS, and we also discussed the end effects. Ongoing and future work includes validation. We're constantly doing validation of BECAS and all the different models we are developing. We are hoping to do fatigue analysis using stresses and strain energy release rates on wind turbine blades. Once again, the gain in computational efficiency allows us to do this. We have recently developed layered elements inside the BECAS. We are now on the implemented. It's been implemented. We need to just make it sufficiently organized so that it fits the stable version. And we are looking into pre-twist and curvature corrections for the cross-section properties, and soon we'll be looking into tapering. We are going to continue the work we have started on structural optimization, and that will be still down the topology optimization way. to include more sections along the length and their elastic constraints. We are looking into how we can do estimations of buckling, panel buckling inside BECAS. Often an aspect of this type of tools is the integration with other design tools. So the pre and post-processing phases are very important to make these tools useful. We're also looking for any new ideas you may have. So please come forward and write us if you have any ideas. So thank you so much for listening. And you can go to www.becas.ttu.tk for more information.